Hey guys, this is Mr. Y. For this video, I would like to go over lessons 1.1 and 1.2, meaning we're going to go over the classwork and homework for both lessons. And hopefully you can use this information to review for your upcoming quiz and kind of make sure that you understand the concepts well. So starting with option A, or actually scenario A, a plumber charges a fixed fee for coming to your house, then charges a fixed amount per hour on top of this. So, and the question is, how much does the plumber charge for a 3-hour job? So for this question, because we don't have the information, we don't have the rate, we don't have the fixed fee, we're not going to be able to answer it. But as you know, we've completed a future question that is similar to this one. Actually, it's exactly the same, but with that information given. So the question here, however, is not asking to write an equation. It's asking us to match the scenario with the graph. So which graph goes with which scenario? So because we have a plumber who's charging a fixed fee and then a specific fixed rate, that automatically tells us we're using a linear equation. That's what linear equations are known for, linear graphs. They're known for their slope, which is the rate of change, which is constant. It's a fixed number. So therefore, automatically, we know it's either option 2, option 5, or option 3. Those are the only linear ones. Now, option 2 starts at 0. We know this plumber charges a fee before showing up. So that's not going to be it. Option 3 shows a linear equation, but it does not show that the rate is going, or actually the fee, as the total cost as this plumber works goes up. It actually shows a line that is descending. So that cannot be it. So for this reason, A should go with option 5, or number 5. So 5 shows a starting fee and then a constant rate of change. And that's what A describes. Part B, cycling. A cyclist travels along a direct route from town A to town B. We talked about this in class. When you're traveling, at the beginning, you're farthest from a point, and at the end, you're closest to the other point or farthest from the first point. And because the distance is changing, it starts at the farthest and again in between, they're at equal distance, and then and so on. Then again, it's linear. And what matches this is graph 3. For B, so it's number 3. For C, internet cafe. An internet cafe charges a fixed amount per minute to use on the internet. So this is again linear. There's a fixed amount. We're not charging an additional fee. We're not charging an, let's say, entrance fee to the cafe. So we know automatically that this is linear and it starts at 0, 0, meaning that if you use the internet for 0 minutes, you'll pay $0. And for this reason, option or graph 2 represents this scenario. For part D, cooling kettle. A kettle of boiling water cools in a warm kitchen. So again, we start at a high temperature, so it cannot be here because that doesn't start at a high temperature. And again, we already used options 2, 3, and 5. So we have 3 scenarios left. Cannot be 4. It cannot be 6 because 6 starts somewhere and it goes up. So the temperature doesn't, increase. The temperature, the kettle cools off. So it has to be option 1. Option E, a man blows up a balloon. With time, as that person blows up the balloon's volume is going to increase, and this represents graph 6. And then lastly, F, height of a golf shot. The height is normally goes to a maximum and then drops back down. And the picture or the graph that demonstrates that is option 4, is graph 4. So I hope this helps you understand the types of graph that are associated with scenarios. Let's move on to the next page. In this page, you have a graph that shows time on the x-axis, or on the time axis in this case, and speed on the y-axis. The first part of this question says, so the graph shows the speed of a car during a trip. The first part says, describe the car's changing speed during the trip. So if you monitor the motion here, right, what's happening here on this graph? Up, flat, down, flat, up, flat, down, flat, and so on. So we're gonna say, to follow this motion, it's an increasing, and I'm gonna abbreviate that, increase, then stops, right? Increase, stop. So if you see that the speed is not changing, you know here, you're at this constant speed of 60 miles an hour. So the motion for that is, or the description for that is stop. So increase speed, stop, decrease speed, stop, increase speed, stop, and so on. So we're gonna write this down. Increase, stop, decrease, DEC for decreased, and it's okay, you can use decreased, DEC, or decrease on your quiz, and then stop, and then after the stop, increase, stop, decrease, stop. So we said increase, stop, decrease, stop, then increase, stop, decrease, stop. We're here now. We have increase, stop, decrease. So we have 3 more steps: increase, stop, and decrease. This is the motion. This is the description, period at the end. This is the description of the motion. Now, when is the graph, the car stopped? So we have for part B, when is the graph stopped? We're stopped, and I'll probably use the letter B for that. We're stopped here. We're stopped here, 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 and be careful, those we almost missed them, and here. So we're stopped between what? We're stopped from left to right again. We stopped between 9:10. So notice the stop is here, from here to here, okay? Should be more vertical. And then the stop is here, the stop is here, and the stop is finally here. So remember, the intervals are X values, or in this case, time values. So we're stopped from 9:10 to 9:20. We're then stopped from 9:30 to 9:40. We're also stopped between 9:50 and 10. And the fourth and last stop is between 10:10 and 10:20. The second part, or the third part of the question, is when is the car speeding up? So when is the graph going upward? And we can see that the graph is going upward here. It's going upward here, and it's going upward here. So technically, there are 3 intervals. Those are X intervals, okay? So it's between 9, from 9 to 9:10, the graph is going up, comma. From 9:40 to 9:50, the graph is also going up. And lastly, from 10:20 to 10:30, the graph is going up. And so this is the graph going up. I think I forgot to stop here. Yeah, I just saw it. You see, I forgot to stop. This is also stop. We have from 10:30 to 10:50. 10:30 to 10:50. If you're watching this, you probably are correcting me ahead, right? So from 10:30 to 10:50, that's also a stop. So again, I would label them again. What's a good way, right? This is a good learning moment. What's a good way to not miss this is to kind of highlight them. So 1, 2, 3, 4, 5. I didn't do that, so I kind of missed one. Now I have 1, 2, 3, 4, and 5 intervals, time intervals. Those are the stops. Okay, now part D, when is the car slowing down? So let me try to use a different color. Car is slowing down, that's here, that's here, and that's here. So we have 3 intervals for slowing down. And once you're done, you can see that you've covered the entire graph. So slowing down between this point and this point, that's from 9:20, this is 9:20 to 9:30. And then it's slowing down again from 10 o'clock to 10:10, and then, which is this part. And the last part is from 10:50 to 11. Okay, and then the last part of the question, what do the flat parts represent? What do the flat parts represent? The flat parts represent, so the flat parts represent the time intervals, right? It's not just time, it's time intervals for which for which the car is at a constant speed or maintaining its speed. Now, we're not saying all these speeds are the same, but we're saying the flat parts. So for example, the first part B is at 60 miles an hour. It stays there at 60, then it drops to 0, stays at 0, and so on. Or you can say at constant speed or maintains its speed. Either way, it's fine. Okay, so this is really number one. For vocab, discrete versus continuous, we kind of talked about discrete, and we represented discrete by single dots separated. And then for continuous graph, we said you start drawing, you keep your pen or pencil on as you go, and then you stop. Unlike discrete, you move, you draw a point, you move your pen or pencil, you draw another, you do the same thing, you repeat the same process. So we're interested in variables that may be discrete, and I'm going to separate this by a line. So some types of variables that are discrete that show this pattern, right? We learned about a problem that had the number of handbags in it, and we'll get to that at one point. So this could be discrete because for handbags, you go by 1, 2, 3, 4. You don't go by one, you don't go by half. You cannot get a fraction of a handbag. So you go by basically whole numbers, 0, 1, 2, 3. Maybe the number of people is also a discrete variable. It could be something that, again, anything that can be counted by ones and only by ones, like the number of homes. This could be discrete. Whereas continuous, a good variable to remember is time. Time is continuous. So even if we have the x-axis labeled 0, 1, 2, 3 seconds and so on, or minutes, then we still know that we have time values in between them. Unlike the handbags, if this was handbag, you would have, 0 handbag costs $0. 1 handbag costs $50. Okay, and so on. 2 handbags cost $100. So you know this is going to be discrete, the handbags versus the time, right? So I'm going to erase the handbag example here because we're dealing with continuous now. So this is pretty much vocab for or things to remember discrete and continuous graphs by. Moving on. Now, sketch a possible graph for each situation. For part A, it says movie subscription. You get two movies for free, and then you get charged at a fixed rate per movie. So how does this work? If I were to write the number of movies here, always try to label the axes. If they're not labeled, this is the number of movies, and this is the cost here. This is the dollar amount. For movies, we have 0 at the origin, and then we have 1, 2, 3, and so on movies. We don't know how much we're getting charged at one point. We're just knowing that we're getting the first 2 movies free. So basically, if we're getting the first 2 movies free, that means for 0 movies, you're paying $0. For 1 movie, you're paying $0. For 2 movies, you're paying $0. And then let's assume that you're paying $1 per movie after that. Let's assume, okay? So at 3 movies, you're gonna pay $1 only. At 4 movies, you're gonna pay $2, and etc. So the idea, the point of this is to show you that this is an example of discrete values of a discrete graph. Part B, real quick, cup of coffee. A cup of coffee cools in a warm diner. And we had an example similar to this with the water or the tea kettle, previous example. In this case, it starts somewhere here, you have a temperature, and then it cools off, right, until it reaches maybe room temperature. And you can see that this is why this is continuous. It's a continuous graph. versus the graph above, which was discrete. Okay, so feel free, I think this is nothing. Feel free to kind of pause, go back, review, revisit the concept if you need to spend more time on it. Moving on to the next page, page 3, matching activity. We have 5 different scenarios with Ken, and it says match each scenario with to the correct graph. So option A says Ken ran from his home to the bus stop and waited. He realized that he had missed the bus, so he walked home. So I want you to identify keywords here real quick. First, he runs. So the first part, there's running, which means a steeper slope. And then he waits, which means that we have some sort of flat area. And then he realized that he missed the bus, so he walked. So this is kind of like slow here, versus here, ran is fast. So fast is steep, and slow is not as steep. So looking at the options, and let me maybe make the graph or the page a little bit smaller so you can see all options. Which one of the 5 options is represented by scenario A? So if he ran and then stopped and then walked, then we're looking for steep, flat, less steep. And I don't think it's 1, 3, or 5, because none of these 3 exhibit this type of information. So it has to be either 2 or 4. Because we started with running, so we need to pick the option that starts with a steeper. Remember, steeper is like harder to climb. This is a steeper than this. This is less steep. Okay, less steep means it's easier to walk on it. It's easier to climb it. Steeper, it's going to be harder to climb it. Okay, so sharper, more slanted, basically. So for this reason, the first scenario is 4. Then for B, it says, after the party, Ken walked slowly all the way home. So Ken walked slowly all the way home. There's no different motion. There's only one motion of walking. And I would see that this is associated, by the way, this is 5. The number is away from the graph a little bit. I would associate this with graph number 5, walking slowly, right? Walking slowly back home. C, Ken walked to the store at the end of his street, bought a newspaper. So there's like a resting moment here. There's like a stopping moment. And then there he ran. So this is kind of reversed than A. He walked, stopped, ran. So now we're going to go slow, stop, fast, a little sharper. And for this reason, C is 2. Option D, this graph is just plain wrong. Ken cannot be in 2 places at once. So which one? We have actually 2 graphs left. We already selected 2, we selected 4, and we selected 5. If you look at 1 and 3, we can see that for 3, this is a time where Ken is at a certain distance, and the same time right above it, Ken is somewhere else. So this exactly represents the scenario for D. So this is 3, and the last one will be 1, but let's make sense of it. Ken went out for a walk with some friends. Ken went out for a walk with some friends, He suddenly, so suddenly is an indicator that there's no period of stoppage. There's no flat area. And then he suddenly realized that he had left his wallet behind. He ran, so this is a little bit sharper slope, to home to get it. And then what? He got home, he caught it basically. He got the wallet or whatever, he forgot he had the wallet. And then he ran back to catch up with his friends. Okay, so these are the scenarios. Please make sure, so the last one is basically number 1. Please make sure you understand them, right? You understand why they are the way they are. Next is 1-1 homework. So for the homework, I'm going to go over this quickly. We did this in class. The graph shows, let me zoom in here. So the graph shows the attendance at a hockey game and the rate at which the fans enter and exit the arena. Compare segments 1 and 2. What happens for segment 1 and 2? Segment 1, people are entering, and segment 2, they're actually entering. But there's a difference in in the rate of, or the speed of how many people are going in. So for segment 1, or in segment 1, people are entering at a faster rate than that for segment 2. Okay, because you see from at 1, the line is a little bit sharper, it's more slanted, it's harder to climb. So there's, they're entering at a greater rate, at a faster, or I would say at faster or higher. At a higher will be nicer to say higher, better. At a higher rate, right? In more numbers. For number, what do they represent? This is compare. They represent. We just said it. They represent the, how much, right? At what rate are people entering the arena? Number 2, what does segment A represent? 8 represent in terms of the game. Segment 8, you can see that the number of people is decreasing, and it's decreasing at a sharp turn. So it represents, or segment 8 represents a period of time when fans are exiting the arena. And we have to be careful because how fast and how slow things are relative terms. So we can say at a fast rate, but that's fine. They did not really want that. They just said, what does it represent? It represents a time or a period of time when fans are leaving or exiting the arena. What is the significance of segments 5 and 7? Notice 5 and 7 are flat. So during these 2 segments, or in these 2 segments, no individuals or no people are entering or exiting the arena. Okay, no adding numbers or no losing numbers of people. What does segment 6 represent? Segment 6 is a small dip going downward. So segment 6, or it represents a period of time. I would say and again, you know how I am careful with the terminology. Let's say a short period of time. Remember, short and is a relative term. Short period of time when the fans are exiting the arena. Okay, so this is these are numbers 1 through 4. Moving on, use graphs A through D for exercises 5 through 8. It says Janelle alternates between running and walking. She begins by walking. So we have to make sure we understand the setup. The beginning is walk. So we start by walking, then for a short period of time, and then she runs. And these are the same amount of time, basically. They said that. And then she takes a break. And then lastly, walks. So less steep for walk, more steep for run, break is flat, and walk is less steep. So which of these 4 options represent, which graph, for number 5, it says, which graph best represents the given situation? So look at the graphs. A is not it, because A is a constant rate, it's linear. And D is also not it. It has to be either C or B because of the changes in, or the variation in the slope value. So because she walks first and then she runs, so it has to start with a slower slope or less sharp slope. This slope is sharper than this. So because of that, we're not going to choose B. Instead, we're choosing less sharp. So this is walk, and then more sharp, right? More slanted. This is what? Run. And this is what? This is a break. And this what? This is walk again. You can see it's a slower pace. So number 5 is C, option C. Number 6, describe the graph of describe the other 3 graphs. So we can say for graph A, you have a constant rate. Maybe they're walking at a constant rate, or she's walking at a constant rate. For graph B, I'll put all the description on the graph. This is she runs, walks, I would say walk or jog, somewhere between runs and less fast than runs, and then stops or break. And then last one is also sharp, so that's probably a run. And for part D is a little tricky. Starting technically somewhere at 0. And this is what we call like an exponential graph, which we will get to at one point in this class. So an exponential graph means it starts slow and it picks up. So maybe this could be something like starts slowly, or walking slowly, by walking slowly. And then what? And then increases speed as time goes by. Okay, so kind of like, I don't want to necessarily say it a sprint, but slow to fast at an exponential ratio. This is number 6, the descriptions on the graph. Moving on to the next item, which is page 5 now. Number 7, what if Janelle began running, then slowed down to a walk, slow to walk, stopped, and then began running again? Which graph? If you recall, this was the opposite graph, the other graph, right? In this case, it would have been graph B, because that's fast, right? Then slow, then stop, and then run again. So that would be B for 7. It's B. Let me go back here. We can say B for that. 8. What are possible situations for graphs A through D? Use graph A through D, A through D in exercises or for exercises 9 through 11. So during the winter, the amount of water that flows down a river remains at a low constant. In the spring, when the snow melts, the flow of water increases drastically. Remember, increases drastically, that automatically tells us it's B. So this is increases drastically. Okay. And then until it decreases at a steady rate. Oh, so this kind of thing is just by itself, but remember we have more description. So this is not it. We have multiple things. We have first constant, and then we have increases drastically, and then decreases as steady, and then slowly decreases through the fall into the winter. So we have to be careful. It's because there are changes, it cannot be B and it cannot be C. B and C, B is exponential and C is steady, is the constant rate of change. So it has to be A or D. And then question 9 says, which graph best represents the given situation? So which graph represents this? Think about it for a moment. Remember, we have flows down a river, remains at a low constant. And then in the spring, the flow increases drastically. So the second part is going to be increase. So I'm thinking there's here steady, and then the increase is drastic. Right? And then it decreases at a steady rate. And then what else? After that, it decreases through the fall into the winter. So the last thing is decrease, cannot be this. It cannot be going up at the end, right? So for this reason, it's option A. Describe the other 3 graphs. I kind of did at the beginning for this one. This was an increase. This is an exponential. And you don't need to say exponential. This is a continuous increase. This is a continuous, you can say exponential increase or just increase. Exponential means the rate is not the same. Here it's going slow and then it's picking up. Okay, and this is at a constant. What's happening here from winter to fall as the seasons change, what's happening to the numbers of gallon per second? It's increasing at a constant rate. This is a constant rate. So this is increase at a constant rate. And then lastly, part D, it's basically this is flat, which means there's no increase or decrease, right? So this remains here. This remains at a certain level, and then it decreases at a constant. When I say decrease at a constant, that means it's a linear, and then it remains again at the same, and then this decreases drastically. This is decreases drastically, DEC, drastic, and then what? Increases drastic here, right? Increases drastically in the exponential. This is increase in drastic. So keep that in mind, and this is the description here. We just provided this on the graphs. Number 11, make sure you have all these notes. You can pause anytime. Number 11, what are possible situations for graphs B, C, and D? So let's take a look at them. Oh, we're still previously here. We're still at B, C, and D here. We kind of, let's associate something with B, C, and D. What is a possible scenario for B? What could the graph B represent? This is something that is going up exponentially. Something that multiplies fast. That's what exponentially is. So think about, I don't know if you're taking biology, if you have one cell, the one cell becomes two cells become 4 cells, they split basically. It's called mitosis. And then 4 cells become 8 cells. So basically they double. If you think about them, let's say every day, right? You start with 1, and then after 1 day, you double the cells. After 2 days, you double your cells. After 3 days, you double the cells, and so on. You will see that soon enough, you're going to have a very, very large number, and this is called an exponential growth. So this could be a cell division. Okay, this is an example. I gave you like a biology example. It could be anything else. It could be other things. For right, but in the case of water and season, what's happening here? I gave you a different example, but in the case of water and this scenario and the seasons, basically, because we have to stay in context, what could be happening here? So as we go, right, from winter, between winter and fall, what's happening? The number of gallons increase at a exponential rate. So there is a lot of what? There's a lot of melting of the water that is happening, right? There's the melting is increasing basically, and that's why the water is coming in. Okay, so that's for part B. For part C, here you can say ice is melting. Let's see, or snow is melting. Snow is melting at a constant rate, or melts at a constant rate. You can say that because the numbers don't change. And then for D, we kind of described that earlier, right? We said steady, decrease, steady, decrease at a fast speed, and then increase at a fast speed. Okay, and we're talking again about the water flow. So remember, when the snow melts, more snow melting means more water flow. Okay, so this is a description of what can be done for parts B, C, or D. Moving on. Numbers 12 through 14, it says 2 children are selling lemonade. They are charging $1 for a cup. They only sell 10 cups. Consider the graphs shown. So you have number of cups on the x-axis and then the profit on the y-axis. Which graph best represents the given situation? So think about what's going on. They are charging $1 for a cup. So every cup that you buy, you get $1. If you look at this graph, this is continuous. This means if I have cups here, it means I can buy 1.5 cups, or I have 2.5 or 2 3/4, which is not possible. So we know that the number of cups is discrete, therefore the graph is automatically represented by dots. So it cannot be C or D. Now, B, notice that the profit increases as the number of cups are sold, as more cups are sold. But here, we know that they're charging just $1. So you buy 0 cups, you pay $0. You buy 1, you pay 1. You buy 2, you pay 2. You buy 3, you pay 3, and so on. And this would be a perfect example for kind of like a linear pattern, but in dots and discrete, and therefore A best represents the situation. B, what situation could the others represent? So kind of we reiterate here, for number of cups, for this one, the value goes exponentially. So that means if you buy 2 more cups, you're going to start charging more. If you buy 3 more cups, you're going to start charging more and more. So technically, you're charging more as you sell more cups, which is unfair, right? So this could be a scenario for we're dealing with number 13 now. For C, I would say it's not possible unless you have extremely great tools to measure something like, oh, I want to sell 1 1/3 of a cup, right? Then I'll have you pay exactly the amount in the middle. Remember, again, the cups are not they're not continuous, they're discrete. So C is not really possible. In theory, it's not possible. In theory, it may be possible. In actuality, it's not possible. D, number of cups. So think about it, which is kind of, D is kind of funny because this is saying if I sell 1 cup, I'm charging, let's say $5. Let's say, actually here it's $1, right? So let's expect this, or just treat this as $1. If I sell 2 cups, I'm also charging $1. 3 cups. So you're basically giving cups of lemonade free. You're giving them away for free after the first cup. If you sell 2, 3. And also on top of that, this is like saying you have maybe a jug of lemonade, then you're pouring, and no matter what you're pouring after the first cup, you're charging only $1. Also notice before the $1 mark. So if you're cup mark, these are cups. If you're basically putting a sip of lemonade, you're charging someone what? $1. This is like saying no matter how much lemonade I give you, I'm going to only take $1 away from you. Whether it's a sip, whether it's a cup, it's a cup and a half, it's 3/4 of a cup, etc. So these are different scenarios. For number 14, is the graph that represents the given situation discrete? We already agreed that it's A, so it's discrete for that reason, and because of the points. 1, 2, domain and range. We talked about this. I'm going to skip this. This was done in class. I'm going to skip this. Just I want you to remember with this is that closed dot is a bracket. Okay. So for example, here real quick, let me see if I can find a better example. So let's do number 3, graph 3. Okay. For graph 3, it says, okay, we're getting the hang of things. Let's identify domain and range. So think about the domain. Domain is where does the x value start and where does it end, if it does. This x value, this point, starts with an x value of 1. So your domain starts at 1. Because it's included, you put a bracket. Where does the y or the x values start and continue to? The x values, if you go to up, the x values continue to go to the right. But because your graph is ongoing, it goes on indefinitely. That means your x values are going to keep going to the right. And because of that, we say what? Infinity. Now, please, please, please do not put a bracket next to infinity. Infinity is a concept. It's not a number. It's not reachable. Range now, how far up and down does my graph go? The lowest value on the graph is this, is -2. So I put -2 here, and it's included because there's a solid dot, which means it's included. And how far up? Well, because my graph goes on indefinitely up, then again, the range is the highest value, which in this case, we cannot reach the highest value, it's infinity. What makes graph number 3 more challenging? What is 3 more challenging than a normal graph, quote unquote normal, of course, that goes like this, right? And we said in class, it's because it has a starting point, but it doesn't have an end point, right? So you can say graph 3, or you can say it has starting point, but not an end endpoint. It could be maybe 2 words endpoint, because it's, yeah, or endpoint and dash point. So this is basically what makes it challenging. Using words describes the rightmost value of the domain. We said in the domain, this is infinity. Infinity, a concept, and not a number that can be reached. And here, technically, it's what? It's like saying all the way to the right, going all the way to the right, if we're talking about domain. For the range, also same idea. If it's like saying all the way, I should have. Okay, all the way. All the way to the, all the way up for the range, right? Okay, so make sure you recall this, make sure you remember this well. Okay, for number 12, what symbol do you think we should use? We already did that. We said it's infinity, rightmost, and the uppermost or the highest, it's infinity. And infinity is like a sleepy 8, okay? It's a stretched out, elongated 8. So this to kind of give you a quick review on domain and range. I'll try, so let's try some of these. I'll try, let's say for this one, let's see the domain and range. The domain, how far to the left, how far to the right? You start at -7 and you go all the way to the right to 4. So you would say, and including both ends. So -7, 4 in bracket. That's how far to the right and left you go. From left, again, you read from left to right and from down to top, okay, bottom to top. Here, for the range, you start at this point, which I believe is -3, and you go up to this point, which is 7. So the range, again, included from -3, 7. For this graph here, the graph, the lowest point is, or the, let's start with domain. Domain means from left. So the leftmost point is -6, and it's included, so it's in a bracket. The rightmost point is 6, but it's an open circle, so it's not included. That means you don't reach it, so you put 6 in parentheses. For the lowest point on this graph, it's this value. It's not included, so it's open circle, or parenthesis, I should say, -6. And for the highest point, it's this point, which is 4. It is included, so it's a bracket. Again, whenever a point is included, whenever you have, remember, you have a solid dot, it's a bracket, or bracket this way, depending on which end, and you the left or the right. And open circle means right, means a parenthesis. Okay, so keep that in mind. And so on. Number, this one here, domain, automatically you go from -2 to 2. They're not included, so it looks like this. Now, don't confuse this. This is an interval. Don't confuse this for the ordered pair, -2, 2. This is not this here. Just be careful of this this point here, this note. -2, 2. This is not -2, 2. It's not this point. This is an interval. You're saying you're going from -2 to +2. Okay, because you don't reach them, you put that interval in parentheses. And then range, the lowest point is here, -3. It's included, so bracket, -3. And the highest point, let me erase here so you can see it. The highest point is this point. The highest point on the graph is this here. This is the highest point, but it's not reached. And what point is that? Remember, we're dealing from -3 all the way to here. This highest point is actually 0. When you're on the x-axis, your y value, remember, high or low is y value. You're 0, but you're not reaching it because of the open circle. So it's 0 open circle. For this, the domain, the x values start at this point here, which I believe is 8, and it goes all the way to the left, all the way to the left. All these points map to the left. So we start from left to right, so we can say 8, right? We can say 8, comma. we say negative infinity, parenthesis, negative infinity, comma 8, and then bracket because we reached 8. And for the range, the lowest value, what is the lowest y value? The lowest y value is here. You map this way, which is negative 8, I believe. And the graph is going all the way up. You can see the graph goes all the way up. So for this reason, negative 8 is included, negative 8, and then comma infinity, not included. Okay, so this is an example of domain and range. Just be careful in how to represent them. For next one, this is going from -5 all the way to the right. So you can say -5, comma infinity. This is the domain. And for the range, the highest value is 7, and the lowest is all the way down. So you always start from all the way down, negative infinity to comma 7. Okay, for this one, the domain is -1, 2, 3. Always make sure you read, you make sure the scale is going by ones or by two. So make sure you don't just count ones, just robotically, right? Here it goes by one. So it goes, the domain, you go from -7 all the way up to 6. But then it doesn't include -7, it doesn't include 6, so we'll put them in parentheses. And for the range, the lowest value here is -9 included, because we reached that point, and the highest value is this point, which is 7. And we reached that point, so it's a bracket. Okay, bracket. Remember, parenthesis, bracket, and brace. Okay, they're different. Parenthesis, bracket, and brace. For next one, for this graph here, notice that the domain, the graph goes all the way to the left and all the way to the right, which means the domain is from negative infinity, comma to infinity. And the range, the lowest value, it goes all the way down. So it's from negative infinity, from down, all the way up to where? All the way up to this point, which is 4. 4 is included, so bracket. And lastly, on page 8, we're doing this graph here. Notice that if you go to the left, you have a graph. So from negative infinity, and if you go all the way to the right, you also have a graph. So from domain is from negative infinity to infinity. And the range is the lowest point, the graph goes all the way down and all the way up. So it's also negative infinity, comma infinity. Okay, if you have questions about this, just please ask in class. Interval of increasing and decreasing. And then the homework, I'll post the homework for the, I'll post the homework as the key for the homework. Intervals of increasing, we talked about this in class. We said, when is the graph going up and when is it going down? Here, the graph is going down here. This is where it's going down. When they say intervals, that means x values, okay, in an interval. And then the graph is going up this way. So you would agree with me that to the left of this point, the graph is going down. And to the right of this point, okay, the graph is going up. So how do you say to the left of this point? So you would say, to the correct terminology, you would say the function, what do we want to call it? F of x or y, here they call it y. Y is increasing, that's to the right, increasing, y is increasing. That's the blue side. On what? To the right of this point. What is this point here? What does this point represent? This is not -5. When we say interval, we're talking about the x value of this point. So we're saying to the right of 0. So as f of x is or y is increasing on what? On, and intervals of increasing and decreasing, try to keep them open from 0 to infinity. That means from 0 and to the right, my y values are going what? They're going upward. That's what the interval of increasing means. And now you're going to say left of 0 in pink, left of 0, left of this point. Remember this point maps here. Left of this point, my graph is going down. So how do you say that? You would say y is decreasing. Left of 0 all the way up to 0, from negative infinity, comma to 0. Okay. Here you have two parts. One is decreasing, which is here. So from this point to this point, remember those are x values. So you would say decreasing on what? On -5, -1, on -5, -1. And then increase, there's no increasing, actually it's flat after that. It's flat from -1 all the way up to what? Up to 7. So you would say constant, because that was the third part, constant on -1 to 7. Okay, and let's move on. I think there's one more question on this page. Yeah, so this one, increasing, decreasing. Did they ask anything else? No, just increasing, decreasing. Decreasing and increasing. For this one, it's, be careful with this one. This is tricky. I'm going to color code it. It's increasing here, and then it's increasing here. Okay, so I'm going to say increasing and then on. When we say increasing, we just learned that we're looking for the x values, right? So from which x value to which x value is it going up? This is increasing. And here, from which x value to which x value is it also what? Increasing. So from -8 to -5, it's increasing. And then it's increasing from 0 to 3. How do I say this and that together? You will put the U sign, which means, which is called union, which means together with, okay? And then for the decreasing, this is the decreasing part. And this is also decreasing. So where is it decreasing? It's decreasing between this point, which is -5 and 1 and 0. So it's a decreasing on -5 to 0, whatever's left basically. And then it's decreasing again from where? From 3 union, 3 to 5, between 3 and 5. Okay, so this is basically the class work for 1-2. Let's see, I believe okay, so homework is short. Let's do it. Let's just do it here. What is the domain for number 1? Domain, range, and so on. Quickly here, the domain is, I'll give you the answers. The domain is -4 bracket -4, comma 1 open, or parenthesis. Range is -2, comma 1. For number 2, the domain is between -2 and 2 open. The range is from -3 open, so 3 here, not included, -3, I mean, all the way up to 5. 5 is closed because you can reach 5. Domain here, from left to right, is -4, comma 4 open, and range is from 0 to 5 also open. You don't reach 0 down here, and you don't reach 5 down up there. Number 4, the domain is from -5, so 5 to the left, -5 bracket, comma. Now here, you're gonna be like, what happened here? I go all the way to -1. Is it included or is it not? If it has 1 dot, solid dot, or a closed dot, and 1 open, then really it does have one of them. Because this is, think about this as blank, and think of this as an actual point. So it does have a point, it does reach the point. So what does it reach? -1, a bracket. And then how far down? -2 open. And how far up? +2 closed, because it does reach 2. Number 5, the domain is -5, comma 4, -5 open, comma 4 bracket. And the range is negative, the lowest point is -4, not included. And the highest point is 5 included. And lastly, for this one, number 6, for domain and range, how far left? -3 included, comma -1 also included. Low to high, lowest point is, the lowest is on the x-axis, which means y equal to 0. So 0 all the way up to 2 brackets. And then the last question on this page and homework for 1-2, and this will conclude this video, is using the graph at the right, determine the intervals where the graph is increasing, decreasing, and so on. So I'm going to color code it again. This right here, the first part, is decreasing. And also this right here is decreasing. So let's start with that. Again, we're looking for the x values, right? We're looking for the x values. So from here to here, it's decreasing from 0 to 2. And then from here to here, from 4 to 6. So how do we say this? We say decreasing. I chose decreasing first. Decreasing, we say 0, 2, union 4, 6. Increasing is when it's going up between this point and this point, and then from here to here. So I'm going to say from 2 to 4, increasing on 2, 4, union, and what else? From 6 to 8. And the last part is, where is it constant? It's constant. Let me choose a third color, maybe green. It's constant here. So it's constant from this point to this point, from 8 to 10, or on 8, 10. This is where it's constant. I hope this was helpful. Please make sure you revisit these ideas and let me know if you have questions. This concludes 1.1 and 1.2.